All right. So an anglerfish has at the end of its line, which is being reeled in at 2 feet per second from a bridge above 30 feet. At what speed is the fish moving through the water when the amount of line out is 50 feet? So in this example, the fishing line is 50 feet out. So what that means is that the fish is out 50 feet on the line, so not from the dock, but on the line. And then if we label this X, Y, and Z, like we label all of our problems, then X would be the distance from the fish to the dock. So we would say that this is X, this is Y, and this is Z. So we also know that if it's 30 and 50, that the missing piece is 40. So the fish is 40 feet from the dock, the fishing line is 50 feet. It's being reeled in. If it is being reeled in, then the distance is closing in, meaning it's shrinking. Therefore, dz dt is negative 2 feet per second because it's reeling it in at that rate. Therefore, that rate is shrinking. Now, when you're fishing and you think about standing on the pier or the dock, is the height of the pier or the dock you're standing on changing? No, it's steady. So dy dt is the height of the pier or the dock you're standing on. That's going to be 0. We want to know at what speed is that fish being dragged through the water. So this little fishy's coming in on the top of the surface of the water. We want to know at what speed is that little fishy being dragged across the water. So we are looking for dx dt. So we have a nice right triangle. If we have a right triangle, we're using Pythagorean theorem, which means we'd need the derivative of Pythagorean theorem. And then we're looking for dx dt. So we get negative 100 over 40, which is really like negative 10 over 4, which is really like negative 5 over 2, which is really negative 2.5 feet per second. Okay. So again, like I said, when we're working through these problems, we're really looking at the geometric shape, what's happening on that shape, and the changes that we are seeing within that. So let's look at the next example. I know I've cut my examples up a little bit, so I want to make sure they match your notes. All right, so we're going to the water tank. Okay. So a water tank has the shape of an inverted circular cone with base radius 2. So it's an inverted circular cone. Therefore, that means it is flipped upside down. So since it's an inverted cone and flipped, we want to think of the top of the cone as up here, and then the liquid leaving the cone down there. It says that the water is being pumped in, so that means that this is filling with water as opposed to draining. And it says that the radius is 2 and the height is 4. So that means that the radius and the height have a proportional relationship. If water is being pumped in at a rate of 2 meters cubed per minute, a rate being pumped in would be 2. It's positive because it's coming in. Find the rate at which the water level is rising when the water is 3 meters deep. So that means that we want to know what is the rate at which the water is rising at a height of 3. So we're looking for dH/dt when h is 3. Well, we need to know our radius. So radius is equal to half the height from the idea that r over h is equal to 2 over 4. So you could kind of like cross multiply that and solve down and see that if you multiply by h, you get r equals half the height. So if the height is 3, the radius is half of 3. If you recall from yesterday, volume of a cone is 1/3 pi r squared h. And we have this relationship that the radius is half the height. So we're looking for dH/dt, so we're going to get rid of r. By substituting in our relationship between r and h. So you get 1/3 pi 1/4 h cubed, which is really 1/12 pi h cubed, which means dV/dt is equal to 3/12 pi h squared dH/dt. Plugging in what we know, 3/12 reduces to 1/4. dV/dt is 2, h is 3, and we're looking for dH/dt. So 3 squared is 9. So you have 9 5/4, so then you multiply that to the other side, and you would get 8 over 9 pi, and our units are meters per minute. So what that means is at a height of 3 meters, the rate of change of the water is 8 meters every 9 pi minutes. So again, that is at a height of 3. The height, or dH/dt, is changing for various heights. So dH/dt is not a constant, it is constantly changing. So if you were to put into words or to justify this, you need to make sure that you put at the specific height at which dH/dt is occurring. So in a sentence write-up, it would be at a height of 3 meters, the rate of change of the height is 8 over 9 pi meters per minute. Okay, so yesterday we talked about rates of change of angles with a ladder. We're also going to look at rates of change of angles with a hot air balloon. So it says a hot air balloon is rising straight up from a level field. And that's important because if the hot air balloon is rising straight up, it's going to form a 90-degree angle with the ground. It is being tracked by a rangefinder 500 feet from the liftoff point. So here's my little tracking beacon. It's 500 feet from where the hot air balloon raised up. It said at the moment the rangefinder's elevation angle is at a rate of 0.14 radians per minute. So what that means is we are being given d theta dt. If you're given radians per minute, that is representative of d theta dt. So d theta dt is equal to 0.14. We know that the angle of elevation means it's with respect to the ground. So my theta in the rangefinder angle is right here. And we are told that the angle is pi-fourths. So that's kind of nice because what that means is that this is a nice unit circle trig value. So it says, how fast is the balloon rising? So if 500 is kind of like my x, this is my y, the change or the distance between the rangefinder and the balloon is never changing, so dx dt is 0. In this instance, we're looking for dy dt. Because we want to know how fast is that balloon rising. So we're going to use good old SOHCAHTOA. In this instance, the pieces of the triangle we're looking at are opposite the angle and adjacent the angle. So the trig function that uses opposite and adjacent is tangent. So we're going to use the idea that tan theta is equal to y over x. We can figure out what y is because we know theta and we know x. So the tangent of pi-fourth is 1. Like that is why this is a non-calculator type question in that aspect, because the tangent of pi-fourths is 1. So you cross multiply by 500 and we get that y is also 500. So what type of triangle does that make this? Isosceles. It's an isosceles triangle. It's a 45, 45, 90. It's an isosceles triangle. Okay? So we want to know dy dt. So once again, we're going to use that same tangent equation. Now, if you look at what we had, we're looking for dy dt. Is it fair to say that y is equal to the tangent of theta times x? Like, are you okay with the idea that we could cross multiply that and say that y is equal to x tan theta? Therefore, dy dt, which is what we're looking for, is equal to the first, which is x, times derivative of the second. Derivative of tangent is secant squared theta, d theta dt, plus the second, which is tan theta, times derivative of the first, and derivative of x is dx dt. But we know that dx dt is equal to 0, so that part of my function is going to go away. And I get dy dt is equal to x secant squared theta d theta dt. So we get that this is equal to 500 the secant squared of pi fourths d theta dt, which is equal to 0.14, which is also the same as 14 over 100. The reason I do that is just because 500 and 100 will simplify to 5. Secant of pi fourths, well, what is the cosine of pi fourths? Root 2 over 2. So that means that this is 5. If cosine is root 2 over 2, secant is 2 over root 2, being squared, times 14. So that becomes 5 times 4 times 14 all over 2 squared, or 2 square root of 2 squared, which is 2. So 5 times 4 times 14 all over 2. Again, 4 divided by 2 is 2, so you get 5 times 2, which is 10, times 14, which is 140. And this is in feet per minute. So what that means is that the rate of change of the hot air balloon when the angle is pi fourths is 140 feet per minute. Okay, give it a second. I was trying to clear the screen. Okay, well, since my iPad screen is freezing, we're going to hit stop share. I might just do the next page of notes with you actually in your note guide. So let's switch to the document camera. And v of t equals t squared minus 1. Find the rate of change at which w changes with respect to time when t is equal to 2. So we are trying to find the rate of change of w with respect to time. So that means we are looking for dw dt. Currently, what is the variable my w has? V. But we know that v of t is equal to t squared minus 1. So we could come up with function composition that says w of v of t would be equal to 2 times t squared minus 1, all cubed. So that would now create a w with respect to t. So w prime of v of t would be the same as saying dw dt, which is the equivalent of 2 times 3 t squared minus 1 squared times 2t. or 12 t squared minus 1 squared. And we want to find this at 2 seconds. So dw dt at t of 2 would be equal to 12 2 squared minus 1 squared. So 4 minus 1 is 3. 3 squared is 9. And then 9 times 12. Right? 4 minus 1. 3 squared is 9. 9 times 12. Yes. Thank you. I was like, I know I'm missing a variable. That's driving me crazy. Thank you. So 9 times 24, well 9 times 20 is 180, and 9 times 4 is 32. So, right, 24 times 9. I can't even think today. So you have your 180 and 36, so you get 216. Well, I said 9 times 4 is 32. I knew I was losing my mind. So you have 216. Is there a different way we could have done this? So the way we did this was using function composition. If you wanted to think of this as a related rate, then what you could have done also as an alternative, and that's kind of where we're getting at, is dw dt. Well, if you took the derivative of w of v, that would be dw dv. And if you took the derivative of v of t, that would be dv dt. So another option that we had would have been to multiply the derivative of w of v, which would have been 2 times 3, or 6 v squared, times the derivative of v of t, which would have been 2t, and then you would alternatively still have had to plug in to 6v squared, our v value, which is t squared minus 1, and you could see how that would again ultimately get you to that line over there. So again, there's two ways you could kind of look at this, and the reason that this is equal to dw dt is because the d of v's would cancel. So again, you could do function composition or related rates, and that's what's kind of a nice culminating aspect of this unit. So example 11, let v equal x, y, z, find dv dt. So this is a product times a product. So when I work on this problem, I typically group two of the variables together and leave one behind. So I think of v as xy times z. So the derivative of v with respect to time becomes the first, which is xy, times the derivative of the second, which is dz dt, plus the second, which is z, times derivative of the first, which is a product rule of x and y. So it would be the first times derivative of the second, plus the second times derivative of the first. So this dv dt would become xy dz dt plus, and then you would distribute your z in. So it's like xy dz dt. So it's x times y, rate of change of z, plus x times z, rate of change of y, plus y times z, rate of change of x. So you'll notice that each side is, since this is kind of like a volume of a rectangular prism, each area of a side is being multiplied by the rate of change of the opposite piece. So like length times width times rate of change of height, plus length times height times rate of change of width. So it's kind of cool to think of this equation in terms of the volume of a figure and how each of the sides are being related to another side as you look at it. Okay, and then the last example with the sphere, since we didn't do a sphere yesterday, is that air is pumped into a sphere at 2 cubic feet per second. So here's my sphere. Air is being pumped in, so we know that a sphere has a volume of 4/3 pi r cubed. It's being pumped in at 2 cubic feet per second, so that's my dv dt. How fast is the surface area changing when the radius is 3? So r equals 3. So in the case of this problem, I have to start with one piece but work to another. So I need to find the rate of change of the radius in order to find the rate of change of the surface area. Because my ultimate goal is dSA dt, but in order to be able to do that, if you think about surface area, the surface area of a sphere is 4 pi r squared. So the derivative of surface area would be 8 pi r dr dt, but I don't know dr dt. So in order to be able to get to dr dt, I am going to have to find dv dt and use that to find dr dt. And what do you notice about the derivative of dv dt? It's surface area. So if you've never realized, the derivative of area and volume are directly related to their derivative before it, just like the derivative of a quadratic is linear. If you took the derivative of the area of a circle, for example, so area of a circle is pi r squared. The derivative of area of a circle is 2 pi r. And then if it was a related rate, it would obviously have dr dt, but 2 pi r is actually circumference. So area and circumference and volume all were originated through calculus and derivatives. Okay, so dv dt is 4 pi r squared dr dt. We know dv dt is 2. We know that r is 3. We're looking for dr dt. So 3 squared is 9. 9 times 4 is 36. So 2 divided by 36 simplifies to 1/18. So we get dr dt is equal to 1 over 18 pi. And then we're going to take that and plug it in over here for surface area dr dt. So we get that this is 8 pi, r is still 3 over 1/18 pi. So again, what's kind of nice is my pi's cancel. And then 3 divided by 18 is 6. So we get 8 over 6 which is really 4/3. And this is feet per second. Okay. So for your homework tonight, I have some like AP type questions. So I'm going to give those to you now. And if you're in physics, you're actually going